Okay, so this video is really going to be the dreaded topic that every student I speak to has probably struggled with this topic. For that reason, pause when you have to, rewind when you have to, and think things through, because sometimes when it's new and it's the first time that you've seen this sort of thing, it's actually quite difficult to get your head around. But we're going to go through it as slowly as possible. I'm going to use examples at every step, and hopefully it will help clear things up for you. And so the first thing that I want to run you through is the idea of relative atomic mass. Relative atomic mass. Now, the reason we use relative atomic mass is because you and I have a mass. The table that I'm working on at the moment has a mass, and we measure those in grams or kilograms, and that's quite easy for us to do. And they're the SI units that we use for mass. However, if we are talking about something as small as an atom, well, there are billions and billions of atoms, trillions of atoms that make up each one of us. And so, if we were to talk about atoms in terms of grams, then that would start to get pretty messy. And for example, a hydrogen atom has a mass of 1.677 times 10 to the power of negative 24 grams. Now, if you're familiar with standard form, then obviously that will mean something to you. If it doesn't, then this is actually how much hydrogen weighs. Okay, here we are. We have this horrendous number with 23 zeros before we reach our 1677, and that is in grams. And so if you've ever held 1 gram of sugar or something like that, you know that it's actually extremely light. Now you imagine being a million, billion, billion times smaller than that. That is what we're talking about when we're thinking about the size of an atom. And so these numbers are obviously no good for us, and there must be an easier way for us to work with the size of atoms. And of course, that is going to be our relative atomic mass. A lot of the time you'll see it given the symbol AR. That just means atomic, the big A for atomic and the R for relative. Okay, right. Now, the relative atomic mass is basically the mass when we give the mass of a proton and a neutron a relative unit. So if you remember, I said we assign a proton and a neutron a mass of 1 and an electron a mass of 0, because it's actually about 1/1840. And so that is so small that we just ignore it and we don't include electrons in our descriptions of mass. And so a quick example, if we have carbon 12, 6, 12, remember, proton number or atomic number and mass number at the top, this has a relative atomic mass of 12. The 12 is basically coming from the mass number. So the mass number is your relative atomic mass. And if you're doing the foundation paper, that is the definition I want you to remember, okay? I want you to remember that protons and neutrons have a mass of 1, and therefore the relative atomic mass is the mass number in units. And so the relative atomic mass here is 12. If we had sodium 23, the mass number here is 23, and therefore the relative atomic mass, surprise, surprise, is 23. Now in real terms, and this really comes into play in the higher paper, and it's actually very important that you know, the relative atomic mass actually takes into account the mass of all the different isotopes of each element. For example, carbon 12 is by far the most common form of carbon. We do have carbon 11, carbon 13, carbon 14, but these are in such tiny amounts that they don't change the relative mass very much. Because almost all carbon is carbon 12, the relative atomic mass of carbon is going to be very, very close to the number 12. And so let me show you how that works in practice. Don't worry if this seems a bit alien, but you'll get it after doing a few examples. if I have a sample, okay, and I have carbon 12, so I have carbon 12, and I've also got carbon 14, okay? If I have 98% of my carbon, 98% is carbon 12, and therefore 2% is carbon 14, I can calculate the relative atomic mass of this sample of carbon. Now there are a few ways of doing this, but I find the easiest way is to think of a percentage as a decimal. And so what I will do is I'll take the mass of carbon 12, which is of course 12, and I'll times it by our percentage as a decimal, which is 0.98. Okay? That's going to give me an answer which is going to be pretty close to 12 because this is almost 1. And what I'm going to do is I'm going to add on our mass of carbon 14, which is 14, multiplied by our percentage of carbon 14 as a decimal. 2% is the same as 0.02. Okay, now you plug this into your calculator and you will get an answer of 11.76 for your carbon 12 and 0.28 for your carbon 14. You add those together and you will of course get an answer of 12.04. And so our relative atomic mass of this sample of carbon is 12.04. You can see because we've factored in the percentages of each one, I haven't just taken an average of 12 and 14, which would give me exactly 13. I've taken the average based on how much of each one I've got. So that means that our answer has turned out just over 12, almost 12, sorry, because almost all of my carbon here is carbon 12. Okay, so I'll give you one more example, which is chlorine. We have chlorine 35 and chlorine 37 as two common isotopes. Now these are actually fairly common to the real numbers, and so this is actually how the relative atomic mass is worked out for the periodic table. So chlorine 35 is around about 75% of our chlorine in the air. And let's say that chlorine 37 is the remaining 25%. Now, please pause the video and use the same method that I used previously in order to find out the relative atomic mass of chlorine. I'll give you a second to do that now. Okay, so I hope you had a go. What we do is exactly the same thing. So we take our mass of chlorine 35, which is of course our mass number, which is 35, and we times that by our percentage as a decimal, which is 0.75 for 75%. And then I add to that the mass of chlorine 37, which is of course 37, and that is multiplied by 0.25. Okay? Now if you work those out in your calculator, you are going to get an answer of 26.25 for the chlorine 35, and that is going to be added to 9.25 for chlorine 37. And that will give you a total answer of 35.5 as your relative atomic mass of chlorine. And if you have a look in a periodic table, most of the time this is the exact value that you're going to see. It's going to confuse people because you'll think, well, how come you can have a mass number which is a decimal point, which has a decimal point in it? And it's because it's the relative atomic mass. We certainly don't have half a neutron in there making up this half, but because we have different compositions of more than one isotope, then we take an average of it, and this is what we use in most of our calculations, because in air, these are around about the proportions of chlorine 35 and chlorine 37 that we are actually going to find. Okay, so I hope that's made sense. Those calculations are very important. They normally will come up, but they are very simple. Once you remember this method, it's the same to work out the relative atomic mass of any element. Doesn't matter. Okay, lastly, one thing I want to mention is that in terms of the scientific definition, to work out relative masses, we have to come up with a reference. And a reference is basically a standard atom that we can use to compare all the other masses to. And what we say is we are using carbon 12. So I'll do this in a different colour. So carbon 12. That equals the standard atom. Now I'm not going to go into why atoms can be very slightly different in terms of their mass, but carbon 12 is the standard that we use. It has 6 protons and 6 neutrons. And that means if we are going to work out the relative mass of one proton, then that is going to be 1/12 of carbon 12. And if you think about it, hydrogen, so the atom H1, has only a mass number of 1, and that is equal to 1/12 of the mass of a carbon 12, 6, 12 atom. Okay, so 1/12 of the mass of an atom of the carbon 12 isotope, if you like. That is our strict scientific definition. Okay, so that's something you need to remember, and it's something you need to write down. You could be asked which is the standard atom that we use to compare relative masses, and that is going to be carbon 12. The reasons behind it are just there are very slight fluctuations in mass of different atoms of different elements, partially because you've got electrons in there as well, which will very, very slightly change the mass. And so we need to have a standard so that everything is uniform. Okay, so I hope that's cleared things up. Please do rewind and re-watch as you like. Now, before we have a look at the explanation of the concept of moles, I just want to quickly go over an extension of relative atomic mass, which is relative formula mass. Relative formula mass. There we go. Now, the relative formula mass is a very simple concept. What all it is a substance which is not only made of one type of atom, will have a formula mass rather than an atomic mass. For example, the elements in the periodic table all have atomic masses, but once you start combining those elements, you get a formula mass rather than an atomic mass. Because even in a pure element, oxygen, for example, is O2. And so the relative atomic mass of oxygen equals 16, but the relative formula mass, which is written MR, so AR is atomic mass, MR stands for formula mass. The MR of oxygen is going to give us 2 lots of 16, which is 32. And so, of course, if we had something else like CO2, CO2 is made of carbon and 2 oxygens. Now, the atomic masses, carbon is 12, and oxygen is, of course, 16, and we have 2 oxygens. So we have 12 plus 2 lots of your oxygen, 2 lots of 16. We've already seen that's 32. So it's 12 plus 32 will give us a total of 44. So our MR of CO2 is going to be 44. Now lastly, something which is less obvious, because if you remember, ionic substances do not contain molecules, but our formula mass, and that's why it's a formula mass and not just a molecular mass, the formula mass is going to be the simplest ratio, and we pretend that it's a molecule so we can give it a mass. So if we had sodium chloride, NaCl, the atomic masses of sodium is around 23 and chlorine is around 35.5. The relative formula mass, well, we have 1 sodium for every 1 chlorine or chloride ion, and so therefore we are just going to have 1 of these plus 1 of these. So it's going to be 23 plus 35.5, which will give us 58.5 as our MR, our relative formula mass. If you had something like calcium chloride, we would have calcium, which has a relative atomic mass of around about 40, I think it's 40.1, And chlorine, obviously, is 35.5. But in the formula, we have 2 of them. And so therefore, we need to double 35.5, which is going to give us 71. Okay, so we have 40.1 plus 35.5 times 2, so it's a bit squished, it's going to give us 40.1 plus 71, 111.1. And that is going to be our formula mass. Okay, so I hope that's cleared that up. It's just a slight advance on atomic masses when we are talking about compounds, molecules, ionic substances, and any case really when we don't just have a single atom. Okay, so now we're going to talk about moles. And from my experience, students probably understand this topic the worst out of almost any topic that you'll come across in GCSE chemistry at least. Once students move on to A level, it seems like they start to grasp the topic. It's almost like algebra and quadratics in maths if you're doing maths GCSE at the moment. There are certain topics which it takes a little while to get used to. But part of that, I think, is because it's poorly explained, especially in your textbook. So in the textbook, you're given a scientific definition and just asked, learn that. However, the scientific explanation isn't really that intuitive. And so I'll give you that first. So you were told that a mole contains the same number of species, so atoms or molecules, so of atoms, molecules, as there are atoms in 12 grams of carbon 12. Now, of course, that is confusing. It is strictly true, but it is confusing because none of that is really very intuitive. It is very scientific and straight to the point. So the way I like to look at it is like this. I'm going to first use hydrogen gas as an example. This is partly because we've actually seen it in previous videos. So hydrogen gas will look something like this. I could draw the dot and cross diagram as well, but I'm going to simplify it and make it quicker. So this here collectively is one molecule of hydrogen gas. Now, if I have 1 mole of a substance, think of 1 mole as being just a standard measuring unit. So if you're cooking, I don't know how many of you are chefs by now, hopefully you are. If you're cooking, then you use measures such as ounces, you use, sometimes you see, add a tablespoon of this, add a teaspoon of this, add a cup of something, cup of water or whatever. And the cup obviously has a fixed volume. If you thought of having a cup of hydrogen gas, move this back, we had a cup of hydrogen gas, let's call that 1 mole. Now this cup can only fit a certain amount of hydrogen molecules in there. So the amount of hydrogen to fill up the cup, like so. This is completely hypothetical, obviously hydrogen is a gas, but this is just an analogy. The amount of hydrogen in here is 1 mole, okay? And that is going to be a fixed number of molecules. Now another example I've used before is carbon dioxide. If I had CO2, that will look something like this. And because it's double bonds to both oxygens, that is CO2. And this is 1 molecule of CO2. So 1 molecule here. If I had 1 mole of CO2, I'm going to have exactly the same number of molecules filling this cup. And this cup is what we're calling the mole. So, wrong colour there. Exactly the same number of molecules as there were in the cup of hydrogen, filling that up. And so 1 mole is literally just the same amount of either molecules, atoms, or fundamental units. And that's when we're talking about things like ionic compounds or metallic. But we have exactly the same number of these molecules in this cup, which is 1 mole, as we do in this cup, which is 1 mole. And so it doesn't matter how many atoms we've got, because obviously there are more CO2 atoms than there are hydrogen atoms. CO2 is also heavier because carbon and oxygen are both heavier than hydrogen. So this cup is going to weigh a lot more than this cup over here. However, they have the same amount of molecules in there. So each one of these is an independent molecule. And that is all a mole is. A mole is telling you a fixed number of fundamental units. And the reason why it's not a fixed number of molecules is because we can also have ionic compounds, and we can also have the noble gases, which are just atoms. They're not made of molecules, they're made of atoms. But if we had 1 mole of something like argon, let's say we had argon, 1 mole of argon is going to be exactly the same. Just fill this hypothetical cup up with argon, and you're going to have the same amount here of argon atoms as you have carbon dioxide molecules and hydrogen molecules. And so that is literally what we mean when we're talking about a mole. In case you're interested, the number of molecules or atoms that we're talking about is 6.02 times 10 to the power of 23. So if you do maths and you know standard form, then that is 6, and then after the 6 there are another 23 spaces before you'll reach a decimal point. So that'd be 602 and then 21 more zeros, so it's actually a huge number. And so why do we use this number and why is it special? Well, that goes back to the scientific definition, because 12 grams of carbon-12 has this many carbon atoms inside. So the way it works is that if you have your relative atomic mass, then a mole of your substance will weigh your relative atomic mass in grams. So carbon-12, you've got carbon 612. Let's say this is our relative atomic mass of carbon. 1 mole of carbon-12 weighs 12 grams. How about hydrogen gas? Well, hydrogen gas is written H2, and H2, obviously each hydrogen has a relative atomic mass of 1. Hydrogen in general has a relative atomic mass of 1. And therefore 1 mole of H2 weighs 2 grams, because we have 2 of these. So 2 of those gives us 2 grams, and then 1 mole gives us obviously 2 grams. Okay, lastly, what about carbon dioxide? CO2. If we go to our periodic table, you can look that up, but I'm going to tell you that carbon has a relative atomic mass of 12. Oxygen has a relative atomic mass of 16. We have 2 oxygens, so we have 12 plus 2 lots of 16, which is 12 plus 32, which will give us 44. So the relative mass of carbon dioxide is 44. So 1 mole of carbon dioxide weighs 44 grams. And so if we had a test tube with 44 grams of carbon dioxide in it, we know that we have 1 mole exactly of carbon dioxide. Okay, so that is what a mole is. Going on to calculations, I'm going to move on with some of those in the next video, but I wanted to take some time to explain exactly what a mole is, use an analogy so it doesn't seem too confusing, and of course if you're still not getting your head around it, keep rewatching the video, or do send me an email or write a comment below and I'll be happy to help as well. So thanks for watching, I look forward to seeing you in the next video.